All right, here are solutions to perfect problem 7 from Math 111. You're given this huge mess of a polynomial and then asked to list all of the possible rational roots of the polynomial. So not all of the roots, just all the possible rational roots. The way you do this are possible rational roots. You don't need to write this. They're integer factors. They're quotients of integer factors of the constant term, in this case 45, and the leading coefficient, in this case 8. That's called the rational root test, or the rational root theorem maybe. So what I'm saying is if we take 45, its integer factors are 1, 3, 5, 9, 15, and 45. Those are the positive integer factors. And 8, possible integer factors are 1, 2, 4, and 8. So we want factors of 45 divided by factors of 8. In other words, we want plus or minus, maybe plus or minus this whole list. Can I do that? I don't want to write plus or minus over and over again. So I'm going to say plus or minus is probably bad notation. 1, 3, 5, 9, 15, 45. So that's all of these numbers divided by 1. And then I want all these numbers divided by 2. So 1 half, 3 halves, 5 halves, 9 halves, 15 halves, and 45 halves. And I wish I had chosen smaller numbers because now I got to divide all of these by 4, quarter, 3 quarters, 5 quarters, 9 quarters. My handwriting gets worse when I get bored. 15 quarters, 45 quarters, and then finally divide them all by 8. In this case, none of these numbers are repeated. You don't have to worry about that. 3/8 is not equal to any other fraction on this list, for example. That's because all the numbers in the numerator are odd, and the numbers in the denominator are powers of 2. 9 to the 8th, or 9 divided by 8, 15 eighths, and finally 45 eighths. So sure, one way you could say it is it's plus or minus this huge list of numbers. They're all possible rational roots. I think there are 24 in here, plus or minus, so 48 numbers that could be rational roots. I didn't want you to test all those, so I told you in number 2 that 3 halves is a root. 3 halves is a root if f of 3 halves equals 0. It does. If you take this polynomial and change all the x's into 3 halves and the thing equals 0, then you have a root. That'll work. I just didn't want you to do this. It seems like a pain to do 3 halves to the 5th power, then multiply that by 8, then subtract 3 halves to the 4th power, multiplied by 12, etc. So that's how you do it. I think that's all you got to write there. Next one says find the other 4 roots. I got one of them, find the rest. And it gives you a little hint. It says because 3 halves is a root, we know x minus 3 halves is a factor. However, we could also say 2x minus 3 is a factor. This is the same as this if we just multiply everything by 2. It'll be a little bit easier to use this guy over here. So what I'm saying is when you do polynomial long division, instead of doing x minus 3 halves divided into, 8x to the 5th, minus 12x to the 4th, minus 46, God, this is going to be horrible, minus 46x cubed plus 69x squared plus 30x, and yes, I'm complaining about a problem that I made, minus 45. Instead of dividing it by x minus 3 halves, divide it by 2x minus 3. It'll work out easier. You won't have to deal with fractions. All right, I want to get rid of 8x to the 5th. I'm going to put a 4x up here because 4x times 2x is 8x to the 5th. Sorry, 4x to the 4th up here because 4x to the 4th times 2x is 8x to the 5th. 4x to the 4th times negative 3 is negative 12x to the 4th. And then I subtract 8x to the 5th minus 8x to the 5th, nothing. Negative 12x to the 4th minus negative 12x to the 4th is the same as negative 12x to the 4th plus 12x to the 4th, which is also nothing in this case. So I get nothing here. If I bring down the rest of the stuff, I get to here. Draw that line all the way across. And now repeat. Find a number you can write up here so that when you multiply it by 2x, you get negative 46x cubed. That number is negative 23x squared. I knew that because negative 23x squared times 2x is negative 46x cubed. Negative 23x squared times negative 3 is positive 69x squared. And we subtract. And what you see happens is these cancel out, and like in the first step, these cancel out also. 30x minus 45. I want to get rid of this 30x. To get rid of 30x, I'd have to put 15 up here because 15 times 2x is 30x, and 15 times negative 3 is negative 45. I subtract. I get no remainder. That's a good thing. What that tells me is that my polynomial, f of x, is equal to 2x minus 3 times 4x to the fourth minus 23x squared plus 15. I can factor this mess over here. Basically what you're doing is a substitution. So let's change colors. Factor 4x to the fourth minus 23x squared plus 15. Let's let y equal x squared, and we have 4y squared minus 23y plus 15. I can factor this if I can find two numbers that multiply to 60, 4 times 15, and add to negative 23. Negative 20 and negative 3 are those numbers. So if I write 4y squared minus 20y minus 3y plus 15, I'll be able to factor by grouping. So what I did is I found the two numbers that multiply to 4 times 15, 60, and add to negative 23, and I replaced negative 23y with kind of those numbers. Factor by grouping, the greatest common factor in these first two terms is 4y. If you pull out a 4y, you're left with y minus 5. If you want to be left with y minus 5 over here, you better pull out a negative 3. I now have two terms that both have a y minus 5 in them, so I can factor that y minus 5 out. And I'm left with just 4y minus 3. But what's y? Y is just something that I made up. It's supposed to be x squared. So I get x squared minus 5 and 4x squared minus 3. So I've now factored f of x, so I can go back to blue here, I suppose. And I can say f of x is equal to 2x minus 3 times x squared minus 5 times 4x squared minus 3. So if I'm trying to figure out the roots, I set that equal to 0, and that tells me that either 2x minus 3 equals 0, x squared minus 5 equals 0, or 4x squared minus 3 equals 0. If I solve all of them, okay, 2x equals 3, so x equals 3/2. I already had that one. X squared minus 5, I get x squared equals 5. So x equals plus or minus the square root of 5. And here I get 4x squared equals 3. So x squared equals 3/4. So x, short on room here, is plus or minus the square root of 3 divided by 2. Square root of 4 is 2. So those are my roots. Hope I'm almost done. Nope, still got to do part 4. Okay. Find the other 4 roots of this polynomial. Here they are. 1, 2, 3, 4. Sketch a graph of this polynomial. Fortunately, we don't have to be too precise in this class because in this class, I don't know, a lot of these things we don't know how to do at this point. Okay, so I have roots. 3/2 plus or minus the square root of 5 plus or minus the square root of 3 divided by 2. Note that the square root of 3 is smaller than 3. So the square root of 3 divided by 2 is smaller than 3 divided by 2. What I'm saying is somewhere I got root 3 over 2. And then somewhere further out I got 3 over 2. And then somewhere even further out I get the square root of 5. And I also need negative root 3 over 2 and negative root 5. Those will be all my roots. They all have multiplicity 1, so I'm going to cross over the axis at those points. The y-intercept is negative 45, because when f of x equals or when x equals 0, f of x equals negative 45. The end behavior, when I go to the right, I go up, and when I go to the left, I go down, because this number is positive and this exponent is odd. What I'm saying is that somewhere down here I got negative 45, and my graph, maybe in green, is going to do something like this-ish. Very, very roughly speaking, it looks like this. There's a lot of things that could be wrong about this graph, but in our class, we just have to make sure it goes through these 5 points, has the proper end behavior, and then goes through this point also. So that is the end of this kind of long perfect problem.